Hello everyone again, I'm Federico Tesser. As Laura said, I'm an HPC specialist at Cineca, and there you can find my email address if you want to send me some insults after this presentation. I don't know, or if you have any question, you can just write to me. Today we will have a little introduction about energy efficient computing, and we'll see some things about that. We'll speak a little bit about Cineca and Leonardo, the new flagship system of Cineca, and we will see an evolution of computer architecture focusing on the energy efficient part, and then I will leave the floor to Andrea for a bit more detailed part on some theory and energy efficiency on large-scale data center, and for the end we will present you some European project of which we are involved, which represent the actual state of the art for the power management and energy efficient ecosystem. So what is a Cineca? Cineca is a non-for-profit consortium. Okay, it is composed by 98 members, and among which you can find 2 ministries, so it's quite important. We have 5 offices, one in the beautiful city of Bologna, and then Milan, Rome, Naples, and Chieti. They also are beautiful cities, but I mean, we are from Bologna, so Bologna is more beautiful. Cineca is composed by more or less 1,000 employees, and it has 3 data centers. The one in Casalecchio di Reno, which is the headquarters, the second one in Naples, and the third one the third one not for power, but not for importers. Instead, it's the more important, and maybe the most famous is the Technopole in Bologna. Okay, cool. Timeline, a little bit of timeline. Cineca supercomputer. Here I represented the flagship of Cineca, just to show you that Cineca has been always at the edge in Italy for what concern supercomputing. Okay, the first supercomputer in Italy went there. The first vector supercomputing, the first parallel system, and etc. etc. We can arrive, more or less 2016 with the more famous system that he got, which are Marconi 100, which now is dismissed, and then Leonardo, actually last year. One slide for Leonardo. Leonardo is ranked for the top 500. He reached more or less 250 petaflops of calculus power, and is composed by 5,000 nodes, divided into partition depending on about your how what your application needs. Okay, one more general purpose, and one more data centric. The racks are cooled actually for their totality by direct liquid cooling, and I mean there is an interconnection HDR to 2000 gigabit, and we have more than 100 petabyte for data storage divide, of course, and with a partition which is classical HDD and a new one based on flash memories. So we enter in more in details. We'll see a little bit the trends toward the architecture of HPC system for reaching energy efficiency computing, or at least try to. Okay, so we start. Long time ago, we see here a graph representing like 50 years of evolution, and we can see that at the beginning, there were no problem regarding power and energy problematics, and we can follow the the Moore's law and the Denner scaling until the first years of the 2000. You see, in fact, that from the 70 to the 2000, we have an increase of the single thread performance, followed by an increase of the frequency, and of course an increase of the transistor. No, okay. We reach a plateau in the first years of the 2000 when the power uses begins starting no more following the Denner law. So from there, people started finding some different approaches, and in fact, you can see that the number of logical cores, or other threads, call them as you want, started increasing. Okay, while the frequency stopped to increase. That's how nowadays when classical CPU is composed. Tons of logical cores with lower frequency for each, but that gives, of course, other problematic, especially for people writing code. No, the famous sentence of Shutter, "Free lunch is over." People now had to think a little bit about how they were writing code, because to obtain good performances, they cannot just have faith in a couple of years for having CPU more with an increased frequency. So with this beautiful long story short, we reached the 2020-2022, where we can see different approaches, to reach the exascale and also continue after the exascale era for the computing system. There are some trends following new materials and devices, which are quite important, but I mean they need their time, and also computational models are of course very, very important, but they need time to be reached and to be feasible to be used. So at the moment, the only way which is actually followed by the most part of the vendors is having more efficient architectures and more efficient packaging. Now we are now seeing superconducting parts, 3D stacking, system on chip, and something like that. And that's what we will see for the next 10 years after exascale system, which also can give time for the other path to be discovered. Okay. Oh yes, sorry, I forgot the magic red rectangle to see that's the actual path. Okay, cool. So here we can see a representation of actually what I have said. No, we started with homogeneous architectures. No, when you have a homogeneous CPU. One near the other, with a more heterogeneous architecture, which are the present today. No, we can see. We have seen CPU and GPU as the first part of heterogeneous architectures. Now we are seeing a system where you have CPU and, of course, accelerator or a specific part, a specific component to take action on a little bunch of a little subset of problems each. Okay. To reach the future, no, there are some things actually which must be discovered. Memory accelerator, hybrid memory cube compared with the HPM, for example, or we will see what trend actually will discover. as I said, no, we are now seeing accelerator or specialization in the hardware, and nowadays we can see subsystem taking action on specific problem. No, so here we can see what I actually just said. We passed from a single power processing unit, okay, at the beginning, to many lighter processing units. Okay, remember the first graph I show you, with the Denner scaling and the Moore law, to very different specialized processing units composed together to take action on different sub problems of set. One important aspect to be considered for energy efficient computing is the data movement energy cost compared with the data computational cost. I mean, we can see in the graph in the blue line the first 2 points for both the first 2 points starting from the left, okay, to the right, for both the lines are the cost which demand per picojoule a flop. Okay, so you can see that in 10 years the cost for operation reduced a lot. Okay, but you can see that no matter that 10 years passed, the energy demanded for moving the data away from the register and the chip is more or less the same. And of course, if we reduce the energy demanded for computational part, the energy requested for data moving become more and more important, no, respect to what it was in the past. Okay, so nowadays the data movement dominates computing HPC workloads, no, and the architecture start to become more focused on these problematics. We can see, for example, solutions, no, like unified memory based on HBM, or or integrated system like, for example, the MI300 that AMD kicked. I don't remember, maybe this year, last year, I don't remember what. Or NVIDIA Grace Hopper recently presented. So vendors, research center are focusing more and more on this data movement topic, because it's quite important to reach also something that's quite fascinating. But I think that at the moment it's a bit restricted in R&D part, or at least not in today lives. Something called in-memory computing, no? So where you have inside the memory some computational part which can give you the possibility to use the memory subsystem not only to access data, but also to act as a CMD parts. So that's to reduce the data movement, no, among the processing unit and the conventional memory. So we will have a processing unit with a computational memory, with computational part specific for some calculation to reduce the in-out data movement. And and in this field, RISC-V will play an important role, of course. Before leaving the word to Professor Bartolini, I will just show you a slide to represent you what a present actual data center is. No? Here we represent the Technopole in Bologna. Which are quite very power huge power plant. I mean, at the moment, no, the data center is based on 12 megawatt with a PUE less than 1.1, but it will be upgraded to 24 megawatt in the next, I think, I don't remember, 2 or 5 years, maybe 5 years, I don't remember. So data center are quite power and energy demanding. That's why it's quite important also see energy efficiency on a large scale data center. And here, if Andrea is ready, I will stop my share and I will start his share so he can speak about that and a little bit of theory about all these things. Okay, there are questions at the moment. I can stop, and if there are, just we can have sometimes later. I